morning, everyone. We were talking about water and progress quite a bit on water, and we had started talking about wastewater. I'll continue with that. Let's go to another approach that is taken to try and simplify some of the problems of wastewater. What happens is that in many plants, what you'll find is that there are different kinds of products which are being made sometimes, and all of that effluent from all the various plants, they find their way into the effluent treatment plant. Of course, in one way it is simple because I have only one treatment to take care of. But many times, because of this mixing of various effluent streams, it can create a problem. They can interfere with one another. Okay, so what ideally would be best to look at is that if you can do some kind of a segregation of the waste streams and do a selective mixing, so that things which are similar, you are putting it together, okay, rather than everything together. Sometimes, if you segregate, it's also easy to, like, say a small amount of some pesticide is going into my effluent, and that's what I'm producing. And next time I'm again taking my raw material in water, maybe I can just recycle the pesticide in case the other constituents do not affect performance in the process. So I can do smart things when I segregate, which is not possible to do once it's all mixed up. So remember, this is a very important approach to take, which is selective mixing of waste streams. Another very interesting thing is that sometimes what you'll find is that, especially when you have segregated your streams, what you'll find is that the waste, which you generate, you might find that actually somewhere else in your factory, you are able to utilize it. Or if you're in an industry cluster, and then there are so many different types of industries, somebody might say, hey, give it to me. I have a use for this effluent of yours. Like, for example, the way we utilized distiller waste from the soda ash plant, and then we could put that in and recover gypsum from seawater. But another person might have some other sulfate, and he'll say, fine, I can knock off the sulfate with your calcium chloride, and maybe I want to do that. Okay, so you could have and you could also take something which they produce, which could be useful. So waste exchange is also another very innovative thing to look at. And for that, you need to have greater awareness of what all is going on and how different things can interact with one another. The third is, you might be a good chemical engineer or a good chemist or a material scientist, but you may not really have the skill to look very carefully at doing a waste audit. And there are people who have been trained in this area. They're very sharp. They can quickly spot what opportunities exist for a waste, or better still, how you might be able to minimize the waste through the audit. In a sense, I would say the chemical engineers are probably the most competent to be trained to do this, because they can look at things objectively and quantitatively. So they might be actually good for doing this actually. So waste audit, and so you might call a factory inspector, and just like we saw Davis, how he looked at the Leblanc process, and that's actually the beginning of chemical engineering. How he proposed concepts around minimizing waste at source as a factory inspector. So you can see he was a person who was well adept at waste audit. And many times what will happen is you can actually overlook very obvious things. And so being practical is important. And I will show you one example of that. Now, just so that you know that segregation is, I'm not talking theoretically. Like, let's say last year, this is a company which is very well known world over for their dye synthesis. And they make all kinds of colors and other stuff also. So, in fact, Mr. Ravi Kapoor, chairman of Cuba, talked to me and he wanted to share how exactly they are going about trying to make their plant into a zero effluent plant. You'll see over here, he's listed out a number of things which they're trying to do. And you'll see at the top of the list is segregation of stream based on COD, hardness, total dissolved solids, which is absolutely at the top. So you can see that segregation is a very, very important, clever, practical thing to do. They, of course, are talking about several other things which they also look at, including trying to recover water by means of RO from the wastewater and then treating the rest of the water. So again, you can see it's important. Let me take you through another example. It's long back, 21 years back. So this company, I think, probably are the biggest in manufacturing denim, all the jeans and everything that uh, you wear. Okay, the denim is probably coming from Arvind Mills, and I think that they were the biggest in the world. So what happened was that these people they'd come and talk to me, or I think I'd gone to their factory sometime, and they discussed a problem. What they were doing was that they were trying to recover water by RO, and they were having problems with doing this. That their energy cost, in doing the RO was very high. So they wanted to see if they can reduce the energy cost. And then I asked them, what exactly do you do? And I said, we have got this stream, that stream, all kinds of things. Over here, this happens. Over there, something else happens. And then I said, and they said that the whole thing basically goes to the effluent treatment unit. And before that, we try to recover the as much water as possible by RO. I asked them that, do you have any streams which are very saline? He said, yeah, we have some streams which are very saline. And then I said, see, in RO, in any case, if you're doing RO and you're trying to get rid of salinity, then one is you are getting a permeate stream which you are reusing, and the other is your reject stream. Now, if on the one hand you had a concentrated stream, if you can just segregate it, then I will reduce my overall TDS of the effluent, and there's no need to do RO of that saline stream. You treat that as a separate entity, because after all, what am I doing? By doing RO, I'm making a concentrate stream. If the one that I'm discharging into my effluent unit is still higher than that, what's the fun? I mean, I'll just unnecessarily waste power. They did that, and in fact, they had told me that they were saving something like I think 30 lakhs a month, and I'm talking about 2000. So I don't know what would be the thing now, and I'll just read it out so that you understand. Refer our discussion in your office on 2nd February. I'm pleased to inform you that one of your suggestions of evaluating the incoming stream of concentration on return, when I inquired, it is found that one of our effluent streams is occasionally coming with very high TDS, even more than RO reject. On inquiring, we found that this is due to some process upset and whatever. Now we have made arrangement to divert the stream whenever it goes out of range, and thus we avoid the extra burden on ETP and RO. This has helped us a lot in reducing the cost and improving the process of effluent and RO plant. It's just a 5-minute suggestion, nothing more, maybe a half an hour discussion. And is it something so earth shattering? Not at all. It's very commonsensical. But many times these obvious things somebody can miss out when you're doing things day in and day out. And perhaps if you have a person from the outside who can think differently from how they think, maybe it can be useful. So this is another example of segregation of streams. Now, this is another very important thing to remember, that when you are designing an effluent treatment plant, and remember that there are certain microbes which are really the ones which are chewing up the contaminants when they are biologically degradable. But what happens is, unless you have got a continuous plant, of course, continuously the same thing will happen every hour. But if you've got batch processes, and also different types of batches being run in the same factory, then what can happen is that you may not actually get a constant volume or the concentrations of the different constituents in your effluent. Then the question is, I mean, how exactly will I design my effluent treatment plant? Because if I have to look at it for peak surges, suppose I say the highest that I'm getting is something like uh, 5 times of my lows, then obviously I have to make a much bigger effluent treatment plant, which may be impractical. So in those cases, what you'll do is that, and you can see over here, say it's talking about different times of the day, and then they're talking about the cumulative inflow volumes. And so they're starting, it's low, it's not really increasing much, let's say up to a point, and then you suddenly see a surge in the volume of effluent, and then again it is tapering off. Let's say assume that the concentrations of the constituents are similar, only the volumes are changing. So what you can do is that you can have what is known as an equalization tank. And effectively, before it goes into the effluent treatment plant, these things go into that holding tank or equalization tank. And then what I do is that I can more or less average out all these variations in flow, and then from here I feed the ETP, the effluent treatment plant. So it would be similar, to N1 V1 is equal to N2 V2. You work it out in that way. That what would be the best way to do this equalization. So this is another approach that people take. You see, there are thousands and thousands of different types of reactions, and each one is producing some effluent. If you try to be very specific about approaches, then it becomes extremely difficult to really do any kind of generalization of the approaches to treatment. But on the other hand, if you look at it objectively, what you find, and this is where some of these waste engineers, I'll send you this book. It's a beautiful book on wastewater treatment, quite an old book, but they're classics. They're really good books. What this person has done is that he has been able to uh, classify all the various ways of treating a waste stream chemically. I'm not talking about biologically, but doing it chemically. So, for example, these are the 6 principles. The first is that if there is some constituent in your effluent which you need to get rid of, see if you can precipitate it out. So if you can precipitate it out, great. We know that, for example, hydroxides of metals or oxides are mostly insoluble. Some sulfides are highly insoluble, like mercury. So maybe you can just precipitate it out. Now, in some cases, you cannot do that. But what you might find is that there are certain constituents which I can treat and convert them into an insoluble gas. And I'm talking about a harmless gas, ideally. I can do that, which would be nice if I can take it out as an, and I need to, because it's going into the air. So it cannot be something harmful. It should be harmless. The third is sometimes you'll find that your effluent is actually like a colloidal suspension, and it's not a homogeneous one phase, although it might look like it. So in which case you can of course try and do a coagulation. We are quite familiar with the way you can do clarification with alum, for example, and so you can look at that as a way of removing suspended matter, but finally disperse suspended matter. The fourth could be there are many constituents which a microbe will not be able to deal with, which is the reason why many times you have to do things chemically. But what can be done is, like I've got a chemical, and I know that the none of the bugs are able to chew it up. But what I can do is that I can do some kind of a preliminary chemical treatment, which converts it into a molecule which now the microbe will be able to degrade. So that's what it says. Reaction to produce a biologically degradable substance from a non-biodegradable substance. So that's very smart. Whereas if you try to do the whole thing chemically, obviously the load on the chemicals that you require would be much higher. You don't want to do that. So you do the minimal intervention, which converts something which is non-biodegradable into something which is biodegradable. Then there is another. Now this is also very interesting. That you see, what happens is that there are some constituents which might be extremely toxic. Try as much as you want. Beyond a point, you will struggle to remove the rest of it. Maybe it has its acceptability is only at the ppb level, not even ppm. Like for example, I remember going to Tata Steel maybe a couple of years back, and they were telling me about their plant and everything, and they generate quite a bit of cyanide, and there's a huge amount of work that they do on cyanide removal. But even then, at the end, they always struggle. So what this is proposing as a principle is that reaction to destroy or otherwise deactivate. It says a chelating agent, but it need not be a chelating agent. It could be like cyanide, for example, is a very strong chelating agent. You can form things like ferrocyanide, ferricyanide. So you can bind it up with some metal in a way that although free cyanide is very harmful, but bound coordinated cyanide is completely harmless. In fact, ferrocyanide is used as an anti-caking agent in edible salt. I mean, strange as it may sound to you, it's completely harmless. So, that would be another way of trying to approach this. Or if you've got traces of ammonia, maybe you can form a complex with ammonia, or traces of carbon monoxide. You might be able to do that. And the final is oxidation or reduction to produce a non-objectionable substance or a substance that can be removed more easily by one of the previous methods. Quite similar to 4 in some ways. Let me give you an example. Suppose people will say, have you seen that stream, that nala? This is absolutely purple in color. There's some dye company which is probably discharging something, and it looks so terrible. And the thought that stuff might get into your groundwater and everything. Now, when you analyze the problem, what you may find is actually that the COD is not very high. That stuff is also actually not necessarily very toxic. But the objectionable part is the color. And the color is what? Color is only a chromophoric effect, right? So if I can destroy that chromophore, then the color may disappear. The compound has not necessarily disappeared fully, but I've just done a manipulation and changed the that particular chromophore into a non-chromophore. So now instead of absorbing in the visible radiation, it might be absorbing in the ultraviolet radiation, and I won't even notice it. So the objectionable substance here could be a dye which is colored, and you are trying to make it non-objectionable by really removing that which is objectionable, which is the color. Actually, this waste area is a very interesting area. You can apply a lot of good logic. You can think very smartly, and remember that waste is something nobody wants to pay for. They see it as a liability. If you tell somebody you have to do this, that, and the other, people will, yeah, not. But when nobody is looking, they'll go and dump it somewhere, which is what happens. They'll go and bribe somebody. I mean, there are all kinds of things that go on. There's no way that could have got so polluted if everybody was doing what they're supposed to do. It's not true. But they will do it if the effect on the bottom line is not so severe. So obviously that's where I think finding simple solutions or practical solutions becomes important. In fact, these 6 principles are so important that over here I've tried to list out from that book various kinds of chemical treatment technologies. I might give it to you as a question and say, you tell me in which of these 6 principles it will fall. You can see alkaline precipitation of metals. Obviously, it means reaction to produce an insoluble solid. Then we will see alkaline chlorination of cyanide. It actually forms a gaseous substance. So it will come in 2. Chemical coagulation. Obviously, it will come in 3. So for all of them, you can actually classify, and you'll find that it will fall into one of these 6 categories. And remember, I'm talking about chemical methods of treatment. I'm not talking about biological methods of treatment. Now, this is another very important thing to mention. There is a concept which is known as principal treatment, and there is another which is known as non-principal treatment. Now, what principal treatment means is that, say somebody has told me that you have got chromium in your effluent and you better get rid of it. Chromium is a heavy metal, it's toxic, and you better get rid of it. Otherwise I will not allow you to discharge your effluent. And otherwise everything else in your effluent might be okay. Maybe the BOD, COD, those kinds of things are okay, but it's these heavy metals which might be coming in the way. And then, somebody, you may say, chromium, it should be possible to separate it out by precipitation, at least much of it, not all of it. And so then there are these plots, okay, and you can see that most of these elements, they will have a particular pH where the concentration in the water may be least, and after that again it can rise. In other words, many times you have seen about these amphoteric effects, right, which you have where on either side the solubility can be higher, and sometimes what you might see is that there is a very sufficient segregation, like iron and these other ones. Iron actually, even at pH 5, it will precipitate out, but these ones may require more of an alkaline conditions. So it should be possible to separate out iron very cleanly without taking these out, in which case it would have followed the principal treatment mechanism, where my focus was on removing iron, and I removed iron. But suppose I were targeting chromium, and I tried to aim for the lowest concentration, and so I say, yeah, that is about pH of 7.3. Let's say I can take it out. But the problem is that you can see even copper is going down at that pH. Even zinc, to some extent, there will be a drop in its concentration at that same pH. So what might happen is that you may have removed more than you bargained for. I wanted to get rid of chromium, but also copper and some zinc may have also got removed in the process. Now there is, you might say, hey, that's great. I actually don't want it in my effluent treatment plant. I don't want it in my effluent because I have to discharge it. And so if it comes out as a solid, and I did not expect to remove copper and zinc, but it also came out not bad. But so in a way, it's a good thing. And that would be known as non-principal separation. Means I did not actually target that, but those also came out. But the problem could also be that suppose I could have only taken out chromium, or let's say in another situation, if I could have only taken out copper, then I might be able to sell that copper. I might actually get some value from converting that impurity into a useful material. But then if it is all mixed up, chromium, copper, zinc, then I mean again I'll have to do another separation and nobody might want to buy it. They might say, yeah, I mean, I wanted the chromium, but I don't want it with zinc and copper and everything. So principal method could be a nice method where you are actually intending to then sell your whatever byproduct you get out of it from this treatment. And non-principal would be things which you did not target or actually wanted to avoid, but those also came out. So that's there. Now, and also these kinds of tables are very useful where for different elements, you can try and see what is the best condition under which you might be able to remove these. Like, for example, mercury. It says precipitation as sulfide at pH values between 5 and 8. Good. So I know that that's what I should try and do if I want to get rid of it. So like this, people have worked out a lot of information, and you need not reinvent the wheel. It's not as if you have to start from scratch and do discovery research. People have already done that. So you have to be just smart enough to access information and then try and put it to good use. Is it all clear? Did everybody understand?
Yes, sir.
Okay. Also remember that if I want to precipitate out something, obviously I can't look for very fancy chemicals to precipitate these things out, because your amount may be in ppm, but your volume could be very, very high. And I have to well exceed my solubility product. Otherwise, I can't precipitate out something. So firstly, I have to find things which will give you, as a result of the addition, a very, very low solubility product of, let's say, of mercury sulfide. It has a very low solubility product. So I can add only a small amount of sodium sulfide and it may do the job. Whereas, if my solubility product is high, then I might have to add a lot of these chemicals to get these stuff out in with reasonable completeness, which would obviously increase the cost of chemicals, and moreover, it would add to the effluent load from these chemicals. So you have substituted one problem with another problem. Obviously, you must do things in the smartest possible way and in the cheapest possible way. Okay, let's look at the second approach, which is converting something into an insoluble gas. Say, for example, suppose let's say I've got ammonia. Ammonia is very, very toxic. And for example, in a lot of these shrimp farms where there's a huge amount of ammonia which is found. Ammonia is also not that easy to get rid of, although there are you can use some of the zeolites like zeolite X to remove ammonia, which means that I'll have to obviously have it in a pH where I'm converting the ammonia into ammonia. Or maybe the zeolite X is acidic, and so it can take the ammonia and in situ form ammonium inside. But another approach, maybe it is not necessarily suitable for a shrimp farm, but would certainly be suitable for many factories. You can actually take chlorine, and chlorine, of course, will exist when it reacts with water as HOCl. What you can see is that ammonia is stepwise chlorinated, so it gets converted to NH2Cl, NHCl2, NCl3, and finally it will get converted into nitrogen, N2O, NO3 minus. Now, the nitrogen, of course, is harmless, and so you have converted something which is harmful in the aqueous environment to something which is harmless. Of course, I may also have produced some amount of NOx, like N2O over here. But then, it's like choosing between the lesser of two evils. Sometimes you will see that which is more harmful and which is less harmful, and you may actually choose to do something which is not a entirely 100% a solution, but at least I would say it is good enough as a 90% solution. So I think that that's the kind of practical thing. I remember, in fact, a company called Rubamin, they had this problem of ammonia, and they had never heard of breakthrough chlorination. And I suggested to them that, have you looked at it? They said, no, we've never heard of it. And then they did it, then they implemented it in their process, set up a downstream unit where you can do breakthrough chlorination, and it solved the problem. So you can actually do something around the principle 2. Principle 2 is a very smart, good principle. Look at here also, you can do the same thing with cyanide. If, let's say, I'm at a situation where try as much as I can, I cannot get rid of my last traces of cyanide, you can actually do breakthrough chlorination, and you can see that you can actually, this stuff will ultimately get converted into carbon dioxide, the cyanide, and also some, the N minus, the N in the cyanide will form nitrogen through a progressive oxidation, which I'm doing. So it's a very nice method of converting something into an insoluble and benign gas. But then you
Excuse me, sir.
also, yeah,
So in the an ammonia process, sir, is it
yeah,
NCl3 which is formed an explosive?
no, but what happens is there are some minimum concentrations of substances which will lead to detonation. You cannot have things which are below that concentration, and it will never explode. So when you are talking about in water, you are really talking about ppm levels. Under those situations, these things will never be explosive. Okay.
Okay, sir. Thank you, sir.
So there's always a concentration element to explosion. Okay, but then you have to be careful. Like suppose, let's say somebody told you, I'll form HOCl if I add chlorine to somewhat acidic water, and then you say, okay, I'll acidify my effluent, and you don't know that it's got cyanide, and that cyanide can come off as HCN, which is even more toxic than just cyanide in water. Obviously, if you're going to do this, you have to make sure that you never get into a acidic pH domain. You maintain a alkaline condition. One of you asked, what could be the likely threats? Like you said, isn't NH2Cl couldn't it be an explosive? You're absolutely right. Of course, in this particular case, the concentration would save you. But here, HCN, if it comes out, I mean, there could be a disaster. So obviously, you have to maintain alkaline conditions. So remember, little knowledge is dangerous. Your knowledge should be at least at the level where you can assess whether you are making a bad problem worse. And The best scientists are those who always look at the negative fallout of anything that you're doing. People, who say, I'm an optimist, I always look at the bright side of things. Yeah, okay, you look at the bright side of things, but that's not necessarily the wisest thing to do. I mean, you better look at the not so wise stuff in what you're doing. And then only you will be a good engineer. You must be able to anticipate problems. And the best scientists and engineers are those who look at both the good side as well as the bad side. Those who look at only the bad side or good side, they are going to fail. Again, another H2S. Again, you can do a oxidation with chlorine. It's something like your Claus process, how you can convert H2S into sulfur. It's along those lines, or the Leblanc process modifications. And you can see now with the one reagent like chlorine, look how versatile it is. Look at all the things that it can do. And in addition, of course, chlorine can, because it will become very oxidizing. So it will also get rid of all your bacteria and germs and everything. So it's a wonderful chemical for effluent management. Okay, now let's look at the third principle, which is coagulation. Of course, as you know, all of you know, most of these colloidal suspensions which form, if you were to actually examine the zeta potential or the surface charge on these colloids, what you'll find is that they will have some kind of excess negative or positive charge. And that's what actually makes them colloidal, because there is electrostatic repulsion among these particles. So they cannot come together and become a larger particle. What you have to do is that if you want to neutralize the charge, then you must take something which has an opposite charge to the surface charge of your suspension, and you'll be able to neutralize the charge. And then, because your charges got neutralized, so it will precipitate out. There will be a agglomeration of all your particles. It will form a bigger particle and come out. Now, what you need to remember is the Schulz-Hardy law. Have you heard of the Schulz-Hardy law?
Yes, sir.
So you know that really the coagulation efficiency will depend on the cube of the charge. So for example, if you have got a monovalent ion which you are trying to use for neutralizing your charge on the particle, it will not be as effective as if you say take a trivalent or a polyvalent ion. So obviously the efficacy will depend on the cube of the charge, and that's the reason why certain things are used, especially polyvalent ions, and you can precipitate these particles out. Okay, so that would be another. So I think you've got some feel for the kinds of things that one needs to do to really remove chemically many of these impurities. Now, before the break, let me just introduce you to a concept which I think all of you are very familiar with. Is everyone quite familiar with BOD and COD? Biological oxygen demand and chemical oxygen demand?
Yeah, we have heard about it.
You have heard about it. Okay, good. And that's what it will be. That most of you would have heard about it, but you may not have really studied it in detail. Let's look at what is the definition. The biochemical oxygen demand is a measure of the amount of oxygen that bacteria will consume while decomposing organic matter under aerobic conditions. Most of our effluent treatment plants, they work under aerobic conditions, where you keep sparging air through the system. That sparging is really to put in oxygen which will be required by the bacteria to decompose your matter, because most things, organic matter, will require to be oxidized. Obviously, if your ultimate goal is to form carbon dioxide, then naturally I have to supply oxygen to affect the degradation. It doesn't matter whether it is done chemically or biochemically. The end result is the same, for which I will require oxidizing equivalents, which biologically I need oxygen. Now, chemical oxygen demand does not differentiate between things which can only be biologically oxidized, biochemically oxidized, or between things which are non-biodegradable and can be oxidized. So it is in that way a completely non-selective process. It can chew up any organic matter, and I think all of you would have heard of or be familiar with, say, potassium dichromate, which is a very powerful oxidizing agent, or better still, chromic acid, which is extremely powerful as an oxidizing agent. So always the COD value will invariably be higher than the BOD value, because BOD is only restricted to the portion that can be biochemically oxidized. Okay? Whereas COD is for both biochemical and even otherwise. So obviously COD values are higher, and you can see the discharge norms of, let's say, our Central Pollution Control Board. It says permissible limits for disposal into inland surface waters, on land for agriculture, into public sewers, and for marine disposal. These are some of the norms for inland areas. Like, let's say, the BOD has to be less than 30 milligram per liter, and COD has to be less than 250 milligram per liter. And you can see that the limits for COD are much higher than the limits for BOD. The reason why it is so critical, these things, one is that obviously, I can go and pollute the land, because some of the water can percolate and it can go and contaminate my groundwater, some of these effluents. Okay, so there would be a toxicity sometimes associated with these organics, which can cause a problem. It can even get into the food chain. And for aquatic life, you see, what happens is that if I put all this stuff and let's say some into the water streams, and my bugs are acting, and they start chewing up these effluents, and what will happen then? I mean, it's going to deprive my water of oxygen, because if my water does not get oxygenated, let's say, very rapidly, sometimes you have got stagnant pools. Many times, what you'll see is this algal blooms, which will happen because what's happened is that, it is taking these organic waste, and the bacteria is blooming and growing, and it completely messes up all your aquatic life. So that's why it's so vitally important to be able to comply with these norms. So obviously the most important thing in measuring the BOD is you really want to measure that how much of the oxygen is being consumed by the effluent, because that will really depend on two things. One is that it will depend on the concentration of the effluent, is biodegradability, and the third will, of course, there'll be a time element. Naturally, I mean, it's not an instantaneous process. So the BOD measurements usually take quite long, and it is quite common to actually measure it after incubating for maybe about 5 days. Okay, and after that you see what is the depletion in the oxygen concentration in your solution. So this is what you do. You whatever organic matter which is degradable, could be sewage water, things like that, which normally one can biodegrade, and you take it into some bottle with a fixed volume, typically about 300 milliliter bottle, and then you won't necessarily fill up the entire amount with your effluent. You might, if this BOD level is suspected to be high, then you will put a certain amount, maybe about say 10-20 ml, and the rest of it will be water. So obviously the effluent will get diluted, so there will be a dilution factor which you will need to keep a note of. And then most of these microbes, they also require some inorganic nutrients for their function. So what you'll do is that after maybe you will saturate the solution with oxygen initially, and then after about 15 minutes you can measure the amount of dissolved oxygen, and then you close the bottle and leave it incubating for maybe 5 days. And after 5 days, presumably some of that oxygen would have got consumed in doing this degradation. And so again you measure the dissolved oxygen after 5 days, and then your BOD at time t, like let's say 5 days over here, would be equal to the initial dissolved oxygen minus the dissolved oxygen at after 5 days, whatever you measure, and divided by P, and P is equal to volume of sample divided by volume of sample plus volume of distilled water. And so that's how you will measure BOD at a particular time. Now, what you also need to remember is that the BOD is typically, of course, as I told you, is measured after 5 days. BOD 5 is what most people will refer to. But it doesn't mean that after 5 days that you have necessarily chewed up all of the biodegradable substances in your effluent. You have only chewed up to the extent that whatever was possible within those 5 days. But you need to also know what is the ultimate BOD, which is really like where all of the organics got completely chewed up and formed carbon dioxide, and that is known as the L0, which is the ultimate BOD. So obviously, to reach the ultimate BOD value, you may require more than 5 days. The BOD reaction is a first order reaction, and so I can write rate is equal to the rate constant multiplied by the concentration, or concentration is related to BOD remaining at time t. So at that time, whatever is the BOD. So I take this, okay, and the L0, which is the ultimate BOD, is like also what initially must have been there in my sample. Okay. So then the BOD that I remove at time t, I can write as BOD at time t is equal to L0, which is the ultimate BOD, multiplied by 1 minus e to the power minus kt, where t is your time and k is your rate constant, and these things will be given, obviously, in which case I can equate this, and suppose I know the value at BOD 5, so I can write BOD 5 is equal to L0, the ultimate BOD, multiplied by 1 minus e to the power minus k t. So k will be, let's say over here, the rate constant has been given somewhere. Yeah, k is equal to 0.3 per day, and let's say my BOD value, let's say at BOD 5 days, I calculated it's 200 milligrams per liter. So I'll put that in, and so I can derive now L0. L0 is equal to 200 divided by 1 minus exponential minus 0.3, which is my K, and time is 5. So it would be 257 milligram per liter, which would be my ultimate BOD. Otherwise, sometimes you could be fooling yourself, thinking that the BOD of your sample is lower than what it really is, because what it really is what you will get from the ultimate BOD value. So that's how you derive the ultimate BOD. There are many pitfalls in the measurement of this BOD, COD, etc., and where you need to be cautious. For example, you see, it is not as if that only carbonaceous matter can get converted into carbon dioxide, and that is the only consumption of oxygen. Like, for example, if I've got an amine functionality in my compound, now that also can get oxidized to maybe nitrite or nitrate. So that will also consume oxygen. Now, you don't know whether the BOD due to carbon that you, or whatever you're measuring, what is the relative contributions of other constituents in that BOD. Now, typically what happens is that the carbonaceous matter, its oxidation sets in fast. And of course, it will keep tapering, and ultimately you will reach the ultimate BOD as far as carbonaceous matter is concerned. But somewhere before that, there would be a rise due to the nitrogenous substances which can also get oxidized. So you will need to then find out what is really the contribution of nitrogenous substances to your BOD versus the carbonaceous substance to your BOD. So let's look at this particular problem. It says a secondary effluent has a total BOD 5 of 45 milligram per liter. Now, when it says total BOD 5, means that I did not do anything to segregate the subsequent oxidation of nitrogenous constituents also. So that's why it's talking about total. So it would be total due to the carbonaceous plus the nitrogenous. But simultaneously, they are also running a test in the same way, except that what they have done is that they have put in some, either it could be some chemical, which inhibits the nitrification of your organic compound, so that conversion of that into nitrates, which will again consume oxygen, that is inhibited. So obviously, if I now measure the BOD 5 in the presence of a nitrification inhibitor, then naturally my BOD will be less than whatever is the total BOD. Like, let's say they've done this, and they've done it for two sample sizes, say 30 ml and 50 ml, and the total bottle volume is 300 ml. So obviously, you can understand the dilution factor. Here, when I fill it up finally with 300 ml or total volume, it will be 10, and in this case it will be 6. That will be the dilution factor. And you can see in 30 ml, the initial dissolved oxygen was 8.9. It went down to 6.0 in the presence of the nitrification inhibitor. And in the other case, it was 8.8 and it went down to 4.2. Now, if you run a blank, means there is no chemical. You can see more or less it's remaining constant. So you know that your whatever you're doing is reliable. So now you will BOD 5 with the nitrification inhibitor will be what? Equal to delta dissolved oxygen, which is 8. Like, let's say over here 8.9 minus 6.0, and here it will be 8.8 minus 4.2, and then on the denominator will be sample volume divided by 300, because that's my total volume. So 300 will come into the numerator, okay, and my sample volume if I put. So you'll be able to see, like over here it will be 2.9. So it will be 2.9 multiplied by 300 divided by 30. So 30 and 300 will cancel out. I'll get 10. And so my BOD 5 will be 29. And likewise, if I do it for this, again, I will end up getting quite comparable results. May not be exactly the same, but so you know that your BOD measurements are reasonably accurate. And then once I've got this, I can subtract from the total BOD. And so it will be 45 minus 28.3, which is the average of these two readings. It's 16.7. So nitrogenous BOD would be 16.7 milligram per liter, and your carbonaceous BOD will be around 28 milligram per liter. So that's how you can segregate the different kinds of BODs. Now, of course, what is fundamental is that I must have a way of measuring the dissolved oxygen. So there are different kinds of tests that are known. I'll quickly run you through 3 of the tests. So there is one where, let's say, my oxygen has got depleted, and or let's say I initially saturate and I want to measure. I put in Mn2 plus, and that in the presence of oxygen will give me a manganese 4 plus compound, which is manganese oxyhydroxide, and it's a brown color precipitate. Then I can separate it out, and then I can redissolve it in sulfuric acid, and that will form MnSO4 twice. So it's still manganese 4, MnSO4 twice, and then I can do a iodometric titration and see how much of iodine I required. And then I do a back titration of the rest of the iodine with thiosulfate. And so from all of this, I will come to know that how much was really the amount of oxygen which is present, because 1 mole of oxygen is equal to 2 moles of Mn manganese, MnOH twice, which is equal to 2 moles of iodine, 1 and 1, so 2 will be 2, and then it will be equal to 4 moles of thiosulfate, which I require. So I can get the amount of dissolved oxygen by doing this titration. Obviously, it's a tedious process, and it's also an old process, mostly abandoned. Nobody today does that. There is another very nice method which is quite popular, which is based on fluorescence quenching. There are compounds like this, ruthenium compound, which is quite strongly fluorescent, but it is also known that in presence of oxygen, the fluorescence gets quenched. So you can see as you are increasing the amount of oxygen, this is oxygen is being increased, and oxygen saturated is here. So you can see that the peak is much less. So you can create a calibration plot and see up to which point you get a good correlation between your I0 upon I, which is your initial fluorescence intensity, divided by your final fluorescence intensity as a function of the dissolved oxygen. So obviously, as I goes down, your I0 by I will go up. So you'll get a plot with a positive gradient over here. And you can see at this point, it started deviating. So I would not trust the data beyond oxygen concentration of something like, say, 16 milligram per liter, in this particular case. And also another thing that you need to be sure of is that your intensities do not change with pH, because then it could be another variable. So this particular compound has a very flat pH response. So you can see all the way from pH 10 to about close to about 13, which is great. It's absolutely flat. So it means that I don't have to worry too much about what is the pH of the sample, so long as it is not in these extremities, and then I just read off from here whatever is my I0I value that I get. From that, I read out the corresponding dissolved oxygen. There is another, and this technique is probably the most
So can you
popular.
explain the earlier technique once again? So
This one?
yes, so the quenching one.
Yeah. So what happens is that these substances, if you excite them at a particular wavelength, these compounds have a strong emission. And so over here you can see the emission is around around 620 nanometer. So it's a red emission. And this emission is what you'll get if there is absolutely no oxygen in your solution. But when there is oxygen in my solution, then it is known, that the excited state now has a different pathway for getting coming back, relaxing to the ground state. It may not do it by emission, but it may do it through a collision with the oxygen, and it could be either an energy transfer or an electron transfer quenching by the oxygen. So it can form singlet oxygen, and then the oxygen can relax. But ultimately, therefore, what will happen is that because a lot of the excited molecules are getting quenched by a different pathway, so the percentage which will now emit will obviously come down, and the quenching pathway will become increasingly more predominant as I build up more oxygen. As I have more oxygen, so that other pathway will be more and more prevalent. So that's what is happening, and that's why your emission is going down as you are increasing the amount of oxygen in your solution. Is that clear now?
Yes, sir. Also, sir, can you explain the part where you're talking about the pH?
Yeah. See, I can have a effluent with a wide pH range. Sometimes it can be acidic, sometimes alkaline, sometimes close to neutral, whatever. So what you want is a technique where the emission is not really dependent on the acidity, all right, or the alkalinity of your effluent. So effectively, what this plot is telling you is that the fluorescence intensity for a fixed concentration of this. Obviously, you're taking a fixed concentration of your fluorescing agent, and then you are monitoring this fluorescence intensity over a range of pH. In this particular case, from pH is going all the way to pH 1, and here about 14. Now you can see that in these two extremities, there is a perturbation by the pH, but in this range of around 2 to around 12 or 12 and a half, there is this fluorescence intensity is remaining quite constant. I'm talking about the fluorescence intensity where there is no oxygen. So you are comparing everything under similar conditions except for the change of the pH. You understood? So, then you can be sure that this technique will be suitable at a range of pH. Otherwise, that would become another complicating factor. And the third thing is that you have to make a calibration plot. And the calibration plot is what? Your ratio of your initial fluorescence when you have no oxygen divided by the concentration or the fluorescence for a particular known concentration of oxygen. So I then create a calibration plot, and now if I have an unknown sample with an unknown oxygen concentration, I will just read off what is my value of I0 by I and see where it is coming. Say suppose it's coming here, and then from here I can read off, and I can say that, yeah, so it will have about 11 milligram per liter of oxygen. Is that clear now?
Yes, sir. Thank you, sir.
Okay. And this is the another technique, which is an electrolytic technique. Here, what you do is that there is a cathode, which is let's say platinum, and there is an anode, which is silver, and you've got a salt bridge, maybe a KCl bridge. And then what you do is that you stretch your membrane over the cathode, and this membrane, it could be a PTFE Teflon membrane. Now it has a unique property that it does not allow anything else to get into the electrode except for the oxygen. So the oxygen will go through, and of course it's in contact with water over here, but there is no interference from anything else. It only allows the oxygen to go through. So what you're doing is, the cell potential where oxygen will get reduced in two steps, first to hydrogen peroxide, and then from hydrogen peroxide to water, means hydroxyl ion. These potentials are known. So I will bias the cell at that potential, and so this reaction will happen, and the current that I get will obviously be proportional to the concentration of my oxygen. More oxygen I have, then by Faraday's law, obviously it will consume more coulombs of charge. So from that, I will be able to again, I would have created a calibration plot, and then I will be able to measure my oxygen. And at the anode, because here it's a reduction process that is taking place, at my anode my Ag is becoming Ag plus, and because there's a KCl salt bridge, so obviously it will precipitate and form silver chloride, and that will just form a precipitate, but it won't interfere with the rest of the process. And so this is really the typical cell potential that you have to apply under these conditions, and then you just read off the oxygen concentration. Okay, now let's also look at another thing, which of course all of you know, but still I thought that it would be good to mention it. When you have, I mean, in a plant, you are typically operating with known chemicals. It's not as if you don't know what you're doing. In a laboratory, it's a different situation, because every day you are taking new chemicals, doing research. But in a plant, you might be taking the same thing over and over again. And let's say I suspect that there is some amount of unreacted. Let's say I'm doing a reaction with phenol, and there's some amount of unreacted phenol, and I want to know that what's happening, and whether phenol is the only thing that is contributing to your COD. This is for COD because phenol may not biodegrade. Doesn't matter whether I do it chemically or biochemically. If the ultimate objective is to convert everything into carbon dioxide, then this will be my equation. Phenol plus, let's say, oxygen, 7 oxygen will go to 6 CO2 plus 3 H2O. That will be a balanced equation. Okay, and so you can see phenol has a molecular weight of 94, and 7 oxygens will be 32 multiplied by 7, which is 224 grams. So basically, if I've got 300 milligram per liter of this, then I will require 715 milligrams per liter of oxygen. That means, suppose I'm expecting that there's a solution with about 300 milligram per liter of phenol. Then I can just look at this equation and say, yeah, I mean the COD will be around 715 milligram per liter. So I just have to do the ratio and proportion. And suppose you get a value which is much higher, you will know that there are other constituents which might be also contributing to the COD. So you'll get a quick grasp. These numbers will then start taking some meaning. Otherwise, it just looks like some a number that came from nowhere. It's not that. So I can, for example, it's quite common to do COD measurements like with dichromate. It's one of the most powerful oxidizing agents. That's why it's used. And suppose I have a substance with a general formula of, let's say, CN, HA, OB, NC. Let's say I'm also doing it in the presence of a nitrite inhibiting substance, so that at the end of it, I can get this basically in this form of NH4 plus. That means it didn't get oxidized to NO2. Then I can write this equation that how many protons will be required, how much of dichromate will be required, and what will be the stoichiometries for each of these CO2, water, NH4 plus and Cr3 plus that I've written it down over here. So if you get a general compound, then you might be able to work out for that compound what would be the theoretical requirement of dichromate. All right. So the COD test procedure now, basically just like the BOD, you take it in a COD bottle, and then you take a fixed amount of potassium dichromate, a known amount. You acidify it. You saw that you require acid. You also add a certain amount of silver sulfate as a catalyst. Now, the reason is, you see, I mean, I know that, of course, dichromate can be used to oxidize even an alkane. But sometimes the rate of the reaction might be very sluggish. It might do it, but it may not do it on its own so well. Whereas silver sulfate has been found to be an excellent catalyst, so that even hydrocarbons can be oxidized by potassium dichromate. Of course, you require somewhat forcing conditions. So even with the catalyst, you may have to reflux it for 2 hours. And at the end of it, basically your organic matter has got converted into CO2. And if you used a inhibitor for nitrate, then of course, the nitrogen, you can assume that it stays as NH4 plus. And then what has happened to your dichromate? It's basically gone from chromium 6 to chromium 3. And since it's dichromate, there are 2 chromiums, and each is undergoing a +3 change in oxidation state. So 2 together is 6. And therefore, if I divide the molecular weight of the dichromate by 6, then I'll get the equivalent weight of dichromate. That's what I'll get, and then I'll effectively be able to do the calculations and say what was the BOD or COD from this methodology. So that's what you're doing. Now here again, you need to be very, very careful. Like for example, if I've got let's say some compound which has got, as I told you, nitrogenous species, then it has been found that sulfamic acid is very effective to prevent the interference from nitrogenous species. So in this particular case, I might use sulfamic acid, along with those, and make sure that I'm getting the reaction only due to my carbonaceous substances getting converted into CO2. That's not the only one. You see, if for example I've got halides, like let's say chloride, 2 things can happen. One is that because I'm taking silver sulfate, now obviously in the presence of chloride, the silver sulfate will become silver chloride, and the catalytic activity might get lost. And so you might find that you are underestimating the COD simply because you don't have enough of a rate of reaction. Or it can also happen that because chloride can get oxidized to chlorine by the dichromate, that you might overestimate the COD, and it may be only because of the presence of halides. So huge amount of experience is required in doing this. I know in our own work, I had a master student, and he gave me some COD number. I said, that's absurd. It can never be. And I said, it must be because of some inorganic compounds which are interfering. And then, he checked it by another technique, and then the results were very different. So remember, numbers are only as good as your understanding of the subject. Otherwise, these numbers can be all over the place. And in fact, you can see, like if you have got very saline conditions, there's a special technique. I mean, I was looking at this paper, dichromate reflux chemical oxygen demand, a proposed method for chloride correction in highly saline waters. So, I mean, like if you are discharging something into the marine environment with a lot of chloride or something, and you need to measure COD, and you don't know about the effects of chloride, you will be underestimating, and these pollution control board people themselves will not know all these details. So it's for you really to be very knowledgeable and to point out, all the pitfalls in the measurement. Here, what will you do? Just like in the previous case, obviously I have refluxed it for 2 hours. In this particular case, I'm not doing it with oxygen. I'm doing it with dichromate. And so some of the dichromate would have got consumed and would have got converted into chromous. And so now I do a back titration with ferrous ammonium sulfate. And so obviously the amount of ferrous ammonium sulfate that I will require to titrate the remaining quantity of dichromate will be less than what I started with. And typically, this phenanthrene, iron phenanthrene is taken as a indicator of the redox titration color change in these particular cases. And then I use this formula, which is the chemical oxygen demand is equal to, I have to know my normality of my ferrous ammonium sulfate, and then I have to know what was the amount of ferrous ammonium sulfate I needed for a blank solution, which means it was only the dichromate with no effluent. And then after I've taken the effluent and obviously the chromate has gone down, so I'll see my A minus B, whatever it is, and then this is basically like my dilution factor. This is your volume of sample in ml, which I'm taking. And 8,000 is, if I want to express my COD in terms of oxygen equivalent, because at the end of it, I can express it as this, irrespective of whether I've done it with dichromate or anything. The sum and substance is that it would be like this. So, so what I have to then remember is that like one dichromate basically supplies you 6 electrons. And likewise, one oxygen molecule is undergoing a total electron change of 4, because O2 is going to 2O2 minus, where when it's in the form of water, it's O2 minus. So from oxygen 0, it goes to oxygen 2 minus, and there are 2 of them. So there is a 4 electron process, and its molecular weight is 32. So 32 divided by 4 will basically give me the oxygen equivalents which I required. That's how the 8,000 term comes. And many times you may want to express it in milligrams. Like if you have milligrams per ml of sample or whatever, and then when I express it is in milligram, then of course I will take not grams, like the gram equivalent is 32, okay, 32 divided by 4, which is 8, but when I express it as milligrams, it will be 8,000. So 8,000 multiplied by A minus B divided by the sample volume. So let me quickly take you through 1 or 2 examples. A 50 ml wastewater sample is collected, 10 ml of 0.25 normal K2Cr2O7 is added to the water sample, and 50 ml of distilled water. So 10 ml is the dichromate, 50 ml is distilled water, and 50 ml is your waste sample. Both samples are heated to 150 degrees C for 2 hours. The samples are allowed to cool for 10 minutes and then titrated with ammonium sulfate. The wastewater sample required 15.36 ml of titrant, while the blank sample required 23.65 ml to reach the endpoint. What is the COD of the wastewater sample? So COD will be equal to 8000 multiplied by ml of blank, which is given 23.65, and with your effluent is 15.36. So I'm just subtracting, and then I put the normality of my ferrous ammonium sulfate, which is 0.1015, and my sample volume was 50 ml, and you can see your COD will come to 135 milligram per liter. So that's how you will estimate COD. Now, just to show you that many times, I can express the COD in terms of the dichromate equivalent, or I can express it in terms of oxygen. So calculate COD if 20 ml sample consume 1.6 ml of 0.25 normal potassium dichromate. So potassium dichromate used was 1.6 ml. So 1.6 ml into 0.25 milliequivalent per milliliter, because this is 0.25 normal, it will be per liter, so it will be milliequivalent per liter. So that comes to 0.4 milliequivalent, and this is the amount that was required for 20 ml of your sample, and therefore your COD will be 0.4 milliequivalent multiplied by 1000 divided by 20, and that's equal to 20 milliequivalent per liter. If I want to now express it in terms of oxygen equivalent, then I know that 1 milliequivalent per liter of oxygen means 8 milligram oxygen per milliequivalent. So I'll take 20 multiplied by 8, and that will be 160 milligram per liter of oxygen. So I can express the COD either in terms of my oxygen, all right, or in terms of the MEQ of dichromate. You can just have a look at typically how many electrons are involved in, for example, oxidizing a molecule of glucose, and you can just work out the stoichiometries, and this is the equation that I have already shown you before. All clear?
Yes, sir.